To move on, we need now to consider a 5-electron pair case, but this time we take a case where 3 of the electron pairs are bonding and 2 of them are non-bonding. So let's do that. 3 bonding and 2 non-bonding, and in this regard we take bromine trifluoride, BrF3, bromine trifluoride, as an example of a 5-electron pair case where 3 of the electron pairs are bonding and 2 of them are non-bonding. Let's first draw a little structure. We need first, of course, as usual, to calculate the total number of valence electrons. Well, bromine is a halogen, so it's in the halogens group. It is located in group 7A, so 7 valence electrons from bromine, and there are 3 fluorine atoms, and again, fluorine, just like bromine, is a halogen. It's located in group 7A, so 7 valence electrons from each of these fluorine atoms, so the total will be 28 electrons, 28 valence electrons, in this case of bromine trifluoride. Now if we divide that number by 2, so 28 by 2, we get 14 electron pairs, so 28 valence electrons total, 14 electron pairs in this bromine trifluoride case. We draw the central atom, so that's bromine, and the surrounding fluorine atoms, and there are 3 of them, so that's 1, that's 2, and that's 3. And then we draw a single bond between the central atom and each of these surrounding fluorine atoms, like that. Okay. Now, if you look at these fluorine atoms so far, you would find out that they are surrounded by only 2 electrons, and that's not satisfactory according to valency rules. We need to make sure that each of these fluorine atoms or each of these surrounding atoms obey the octet rule. Each of them has 2, so we need to draw 6 more on each of them. So that's 6 on that fluorine, 6 here, and 6 on the third fluorine atom. And now each of these fluorine atoms or surrounding fluorine atoms is surrounded by 8 electrons, and that's in accordance with the octet rule. Now we calculate the number of valence electrons used up so far in this little structure. You would find it's 8 times 3, that is 24, but we had 28 valence electrons total to start with, so we have 4 to go, and these 4 additional electrons will be in the form of non-bonding pairs or lone pairs. So that's one of them, and that's another. So there are 2 lone pairs or 2 non-bonding pairs around this bromine central atom, and 3 bonding pairs. The next step would be to predict the arrangement of electron pairs or orbital shape, in this case of bromine trifluoride, and since it's a 5-electron pair case, so the orbital shape or the overall arrangement of electron pairs is still trigonal bipyramidal, but the molecular shape may not be trigonal bipyramidal, and that's because there are 2 lone pairs around the central bromine atoms. Now, in order to predict the molecular shape, we need to make a model, and for that, let's take 2 of these bonds off, and if we do that, so that's basically a lone pair, that's another, and these are the bonding pairs, so that's like the bromine central atom, these are the surrounding fluorine atoms, and if you look at this shape, well, carefully, you would find out that it is T-shape. So that's a T-shape, in this case, of 5 electron pairs, where 2 of them are non-bonding and 3 of them are bonding. So let's write that down. The molecular shape is now T-shape, to account again, to account for the presence of the 2 lone pairs of bromine. So to conclude, in the bromine trifluoride case, this is a 5-electron pair case. 3 of the electron pairs are bonding, 2 of them are non-bonding. The orbital shape or the overall arrangement of electron pairs is trigonal bipyramidal, whereas the molecular shape is T-shaped due to the presence of 2 lone pairs around the central bromine atom.